Okay, and on to our final chapter. Now, one thing that is going to be examined in this final assessment, the 20% final assessment, is the three-term Taylor method, which we would have done back at the end of chapter 2. You might, if you skip that at the time, you might want to go back to it after this. Okay. So I have a little quote here, which is the journey for an education starts with a childhood question, and the question is, how does a calculator actually work? Like, how does it know that, say, sine of 30 degrees? It's a bad example. Say sine of 29 degrees. How does it calculate these numbers? How does it do that? Okay, and this is what we're going to look at. You can have a little look at that if you want. We'll be looking at that thing next week. Okay. So a little bit of motivation here, which we probably have kind of covered already, but we'll go through this very quickly. So there's this thing where Top Gear dropped a beetle from a height of a mile, and what it did is it rotated in the air as it fell. Now, if you want to examine the motion of that, you need to know the forces, and the forces would be, I suppose, if we call this plus, we had gravity, which would be mg. We'll draw it over here. Mg, and then there would also be a damping force of the air, which would be given as minus because it's going in the opposite direction. Now the thing about the damping coefficient here, like as the car is on its back like a turtle, that's when it's probably most aerodynamic, and when it's down like this, it's probably least aerodynamic. And so what you're looking at is that the damping coefficient is actually changing in time. So what we're proposing is that as the car goes faster, the air conditioning gets faster, so they're proportional, and the constant of proportionality is the damp. It's not even a constant, it's variable. So minus lambda t, the t signifying that the aerodynamics are changing, times v of t. Okay, if you want to formulate a model, so this lambda is going to have to be a function of time, and maybe it goes something like this. So this is when it is kind of, now I'm terrible at drawing, but maybe from the side on, it looks like that. So the flap bit is at the bottom, and then it's at a minimum when it's like a turtleback. That's supposed to be showing that it's upside down. Look, that's the right way up, and that's upside down. And this could be like, now would it even be equal to this is a very difficult problem itself, but this is just a simple model. So a function with this behavior is given like this. So here you have at the maximum the drag coefficient is big M, and at the minimum the drag coefficient is little m, which is a terrible choice. I'm going to call it max and min. So this is max. I'm going to have to even change it because the problem is I've got two m's. I've got mass and this little thing. But anyway, this function oscillates between the maximum and the minimum. Okay, so then the equation of motion, Newton's second law, mass times acceleration is sum of the forces. Now there's some stuff, it's not actually that important here. We'll learn about it next semester if you do the elective maths. But the acceleration is the second derivative of position. Sum of forces, the gravity force minus the velocity up here is the first derivative of position, and there's your damping. Now, this is a problem that it's even a simplified problem already, because all you're saying about the damping is you're assuming it's a wave. It probably wouldn't be. It would be a more complicated thing than this. But even making that basic assumption and writing down the model, you can't actually solve this exactly. So this is you just don't have, now it's a little bit more like we would have had back in the end of chapter 2, the two scenarios where the first is that the information is given in terms of data, so you need a numerical method, and the other is if you have something you can't anti-differentiate, like e to the minus x squared, you can't anti-differentiate. But this is, you just have no techniques for doing it. It might actually be the case that there is a solution to this. Now, a nice solution. My suggestion is there isn't. I've thrown this into computer software, mathematical software, and nothing comes up. So basically we can't solve this, but you still want to. And the idea is that in engineering this is going to happen. You're going to have problems you want to solve, but you can't solve it exactly. So what you have to do is you need some numerical techniques. You need to do some approximation. Okay. And this is what this chapter really is mostly about. So you want to solve, what does it say? So you can use numerical methods, you get approximate answers, and that's called numerical methods. And say, for example, mechanical engineers would do modules on numerical methods because for them, just so many problems they can't solve exactly. They need to do this. But if you're, so these approximate answers, you have to be able to say that whatever your approximations are good. Now here it says approximation theory. That's actually incorrect. It's called numerical analysis. So numerical analysis is about, and it's hard, is about when you have a way of approximating something. That's numerical methods. Saying how good the approximation is numerical analysis. Now here are the stuff that we really, we may as well talk to it. So suppose your differential equation with a solution, and you come up with an approximate solution. Now h here is like your step size, and you can make that smaller. If you remember back to your Euler method stuff, if you want, you can go back and look at that. You'll have to look at some of it for the three-term Taylor anyway, because it'll be assessed on the final assessment. But anyway, the thing with the Euler's method and three-term Taylor method is that when the step size gets smaller, you get a more and more accurate thing. Now the problem is when the step size gets very, very small, it starts to become a problem for the computer, and the computer can't handle h going to 0. But anyway, so if the approximation method is nice, numerical analysis may come up with some kind of a measurement of the error. Now there's loads of different ways of measuring the error, but in this one it's saying that suppose you're interested in, this was I think a shear force situation. So imagine you've got a true solution. Let's draw something like that. That's true. Now I'm going to exaggerate. So that's a true shear force. I'm going to exaggerate this, and then maybe an approximation. As I told you, I would exaggerate it. And this is looking for between 0 and L. So the black one here is the approx. This is VH. And this is the true one. You want to find between 0 and L where they differ the most. And that's what this error would be. And the idea is that if you make step size smaller, you can make this error smaller. Now you might say, how the hell, like, if you stop and think, you're like, but sure, how can you, if you know the error, sure, don't you know the true solution there? And that's fair enough. But basically, numerical analysis is always kind of looking at the worst case scenario. So usually what you have is what's called an upper bound for the error. You know, the error won't be worse than that. And in numerical analysis, you want to show as well that if you take h to be very, very small, that the errors go really, really small. Okay, so this idea of you've got problems you can't solve exactly, you can approximate them. Theoretically, you can make the approximations infinitely good, but practically that mightn't be possible. You just want to make them good for all practical purposes, and that's what we're looking at. Now this chapter does have some calculus, which you would have done properly in first year, so we're going to do a bit of a review. So we need to talk about second derivatives. Now we would have seen higher derivatives in, like we saw fourth derivatives, but we were anti-differentiating. Here we're differentiating. So we definitely need to talk about second derivatives and actually third derivatives. So start with a function, and you differentiate it once, you get the first derivative, y dash of x, which you might call dy dx. If you differentiate it again, you get what might be called the second derivative, which you write as differentiate twice, differentiate y twice with respect to x both times, and in later we'll look at other things, and you can keep on going, third derivatives, fourth derivatives, etc. I might call this thing that goes from here to here the differentiate with respect to x operator. It's like a function, it has an input and output. Okay, so this generalizes in the obvious way to third derivatives, fourth derivatives. So the issue is you need to be able to differentiate a function. Derivatives of functions, there is at the end of your manual a function catalog, or like you also might use the tables. And the question is, if you combine nice functions, so nice functions are like e to the x, log x, sine x, cos x, tan x, powers of x, roots, these kind of things. How do you differentiate sums or differences? For example, how do you differentiate e to the x plus tan of x? How do you differentiate scalar multiples? So for example, how do you differentiate 6 sine x? How do you differentiate products? For example, log of x times cos of x. How do I differentiate that? Quotients, how do I differentiate x squared divided by square root of x minus 1? And powers, so for example, how do I differentiate, it's written left out here. Surely there's a few more functions knocking around there. We'll just do sine of x. Yeah, just to the power of 5. Roots, how do I differentiate square root of log of x? And compositions, which are more complicated, although not than these, say for example, sine of x squared plus 2. So how do we differentiate these things? And these are the rules of differentiation, which if you go back and look at what differentiation is, you can show where these rules come from. So this one is easy. If it's a sum, you do it term by term. This one is easy. If you have a constant times a function, you fix the constant. This one is the product rule, naturally enough. This one is the quotient rule, when you have a u and a v. And then these ones are the chain rule, which are the hardest. Okay. Now, in previous years, what I've done in this chapter on the exam paper is kind of make the differentiation a little bit easy, because it's basically for a lot of you, you get to third year and you're kind of getting serious now, and like next semester you'll be doing maths that's harder than anything you've done before, and you'll do well at it. But it's funny, the things that'll trip you up, stuff from first year and school like algebra and differentiation will trip you up. And so we don't want you to kind of halt your progress by not being good at the chain rule or whatever. Want to move forward if we can. Like we're finally using maths, which is good. And like strictly speaking, you can ask a computer program to do differentiation for you, but it's still good to be able to do it. And probably, but not definitely, the differentiation that I ask you to do in the final assessment might be a bit harder than the exam questions that we do, although I think I'm possibly going to do one difficult question. Okay. But look, this is all to be seen. I haven't done the final assessment yet. Okay, so let's see these rules. So here they are. Sum rule is easy. Scalar rule is easy. Product rule shouldn't be too bad. Quotient rule isn't too bad. Then the chain rule. Now, the chain rule is the one where people have the most problem, and it's fully understandable. I will probably use certain colors, and even I might go a bit further. So we're going to be, say, differentiating. We're going to have an outside and an inside function. So the outside function and an inside function. And the chain rule says, and this is what it says here, it says differentiate the outside function. So outside, differentiate, and then evaluate at the inside function. So we'll use back here maybe. And that's some of the story, but then the chain rule says you multiply by the derivative of what's inside. Inside derivative, what's inside. Okay, I would probably recommend you, now the truth is you're probably going to be working on your third assignment. I do understand that. There is going to be a bit of a crunch with time for your final assessment. I will make it quite short. Your third assessment's quite short as well. Well, it's not very short, but it's not as long as the others. But I think you should, when you read these, maybe actually just stop now and try some of these. And like you can see some answers here, and if you're having difficulties, do photos, submit your work for feedback. Okay. Right, so we had this question about how does a calculator work. So for example, how does a calculator know how to calculate the log of 1.1? How does it know that? Okay, so addition and multiplication are fairly easy to program, but how about finding the log of 2? So how does it know, like how could it, like I'll tell you for one thing, it doesn't store all the values. Like how could it possibly store that value? It doesn't store, it actually calculates it. So we'll give you an idea how it might do it. So no calculator can calculate log of 2 exactly. That's the other thing, because it's irrational. The decimal expansion goes on forever. Like if you see log of 2 here, that's only so many significant figures. It actually goes on forever and ever and ever. It definitely can't store that. So calculators must use approximations. Even if they store, which they don't, they're still using approximations. Now, if they're being stored, how are these calculated at all? Like, how do you calculate log of 2 before a computer? How can you possibly do that? That bears some thinking about. Okay, so here we describe some methods that we might use to do this. Okay, so first thing is smooth functions. So see the way it doesn't have any jaggedy bits, and it doesn't jump around. They have it's not like the step functions we saw in chapter 2. They have good linear approximations. So we'll talk about all these. So I suppose it's linear and good approximation. So linear there actually just means line. Probably linear isn't even the right word, but we could throw it in there. So near this point that I'm interested in, we could add another fancy word here, local. So local there means near a specific point. So for example, near the point 1, 0. So local to x equal to 1. There's a line. I'm a bit. Oh yeah. So the issue here is that this is not x equal to 0 here. It's just a small point. I don't know why I changed the graph. Just draw the bloody line. Okay. So this, of course, this is the local. It's local to this point. How is it good? It's good in the sense that now you probably can't zoom in. Well, just imagine zooming in. See, when you zoom in close to x equal to 1, the curve and the straight red line are pretty much the same thing. Now, they're not exactly the same thing, so they're an approximation, but they're a good approximation. Now, as you get further away, the difference between them gets bigger and bigger, so it's only a local approximation. And any smooth curve has these local approximations, good local linear approximations, which of course you know as known as tangents. And that's what a tangent is. It's nothing to do with cutting the line or curve at a point. It's about looking like the curve near a specific point. That's what a tangent is. And I'm sorry if this is the first time this has been told to you. So to do this, this is to estimate log of 2. Now we're going to come up with a very rough way of doing this, because remember, we don't even have this graph. But we know theoretically we can draw it. And theoretically, well, how do you know it's smooth? Well, we'll worry about that. Take a point near there, x equals 1. Now we draw the tangent. To get the equation of tangent to the curve, we need a point and a slope. We have a point, so we need a slope. Now the question is, how do you get the slope of a tangent? And you should know that all day long. Slope of tangent is equal to dy dx, to the first derivative. That's what the derivative is for. So we need to differentiate log of x. So if y is equal to log of x, what is the first derivative? Dy dx. You look in your tables or whatever, the derivative of log of x is 1 over x. Okay. And therefore the slope is equal to, so the dy dx gives the slope at any point. And we're actually interested in particular at x equal to 1. So we will evaluate this. This is what this line here means. At x equal to 1. So it's 1 over 1. This is just revision. Slope there is 1. So we can do a y minus y1. Sorry if there's no space here. So y minus y1, what's the y1? 0. Is equal to m, which is 1, times x minus x1. And then all I just have to do is multiply this out. And I get 0 does nothing. 1 by x, 1 by minus 1. So y equal to x minus 1. So that's this tangent. So we have the y coordinates here are equal to x minus 1. And on the curve, the y coordinate is log of x. Now note, when x is close to 1, they are very, very close together. So for example, log of say 1.1 should be very, very close to 1 minus 1.1. Sorry, 1.1 minus 1. So this should be close to 0.1. Not far off. And as we get closer, say, go to here, this should be very, very close to 1.01. This should be close to 0.01. It's very close. You might be able to see it there, but it is. This should be close to 10 to the minus 3, which it is, because it's 10. And as you go on and on and on, it gets closer and closer and closer. And it should converge there. In this case, when you're this close, they're actually, according to the calculator, they're equal. Now they're not actually equal, but according to this, they are, because the calculator does something like this, as we'll explain. So therefore, what we have is for points near x equal to 1, we have that log of x is approximately x minus 1. And we'll write something down here. For example, log of 2. Now this is a rough approximation. Look, we're miles off by now. Should be approximately 1 minus 1. Sorry, 2 minus 1, which is 1. And now it will be a good bit off here, but sure, we'll have a look. Yeah, we're a good bit off, but that's okay. We said when we move away from x, it's only local. But far more accurately, we have that log of say 1.1 is approximately 0.1. Okay. Now the problem is, say if you look at this, how could you get a better fit here? What you could do is you could add a bit of curviness to the tangent. So when I say this is tangent, and I've written tangents for some unknown reason, it really is tangent line. What you could do instead is use a tangent parabola, which is a quadratic. So you could add in a bit of what you might call curvature. And this has the, so this is the tangent parabola. I'm just going to write TP because we're out of space, or tangent parabola. So the tangent line is basically a multiple of x plus a constant, give or take. But the tangent parabola also includes some x squared stuff. And if you remember from ages ago, x squared, you get the u shape and the n shape. This will have a minus x squared shape. Okay, and then you can go further. You could do a tangent cubic, which uses x cubes. You could use x4s, x5, x6. And what the calculator will do is it'll use something like, I'm not sure, but possibly up to x to the 10. So to calculate, say, log of 2, it adds together like 10 numbers. Well, actually it'd be 11, but yeah. So that's how it does it. And you see, as you add more terms on, as you say, use x cubed, x to the 4, this now even this isn't drawn for, it gets closer and closer and closer. And now maybe the approximation is valid, like local, it might be valid, you know, between 0 and 2 or whatever. We can go a bit further if we want to look at that, but we won't be. We just want the basic idea that you can approximate functions like log of x using what are ultimately sums of powers of x. Okay, that's what we're getting at. So instead of fitting a line to the curve, we could fit a quadratic or more complicated polynomial. Now, it says here we're talking about polynomials as in chapter 1. I don't know how much we did on polynomials in chapter 1. And all are somewhat easy for a calculator, or just combinations of addition and multiplication. So for example, log of x is approximately x minus 1 minus a half x minus 1 squared. Now let's see what happens if we use this for log of 2, which is about 0.7. I think what we'll get out here is we'll end up with 0.5, which is a better approximation than 1. Okay. In general, all these polynomial approximations are just that, they're just approximations. However, could you possibly have loads of polynomial approximations that get better and better and better, so that as you take higher and higher powers, more and more terms, that the error to the difference between these two gets smaller and smaller and smaller? That's the question for our next lecture.